Nucleation is the first step in the formation of either a new thermodynamic phase or a new structure via self-assembly or self-organization. Nucleation is typically defined to be the process that determines how long we have to wait before the new phase or self-organized structure appears. Nucleation is often found to be very sensitive to impurities in the system. Because of this, it is often important to distinguish between heterogeneous nucleation and homogeneous nucleation. Heterogeneous nucleation occurs at nucleation sites on surfaces in the system. Homogeneous nucleation occurs away from a surface. Characteristics of nucleation. Nucleation is usually a stochastic process, that is, there is a random element to it, and so even in two identical systems nucleation will occur at different times. This behavior is similar to radioactive decay. A common mechanism is illustrated in the animation to the right. This shows nucleation of a new phase in an existing phase. In the existing phase, microscopic fluctuations of the red phase appear and decay continuously, until an unusually large fluctuation of the new red phase is so large it is more favorable for it to grow than to shrink back to nothing. This nucleus of the red phase then grows and converts the system to this phase. The standard theory that describes this behavior for the nucleation of a new thermodynamic phase is called classical nucleation theory. For nucleation of a new thermodynamic phase, such as of the formation of ice in water below 0 C, if the system is not evolving with time and nucleation occurs in one step, then the probability that nucleation has not occurred should undergo exponential decay as seen in radioactive decay. This is seen for example in the nucleation of ice in supercooled small water droplets. The decay rate of the exponential gives the nucleation rate. It is not just new phases such as liquids and crystals that form via nucleation followed by growth. The self-assembly process that forms objects like the amyloid aggregates associated with Alzheimer's disease also starts with nucleation. Energy-consuming self-organizing systems such as the microtubules in cells also show nucleation and growth. Examples: clouds form when wet air cools and many small water droplets nucleate from the supersaturated air. The amount of water vapor that air can carry decreases with lower temperatures. The excess vapor begins to nucleate and form small water droplets which form a cloud. Nucleation of the droplets of liquid water is heterogeneous, occurring on particles referred to as cloud condensation nuclei. Cloud seeding is the process of adding artificial condensation nuclei to quicken the formation of clouds. Nucleation is the first step in crystallization, so it determines if a crystal can form. Frequently crystals do not form even when they are thermodynamically the favored state. For example, small droplets of very pure water can remain liquid down to below -30 C, although ice is the stable state below 0 C. Bubbles of carbon dioxide nucleate shortly after the pressure is released from a container of carbonated liquid such as Coca-Cola or champagne. Nucleation often occurs more easily at a pre-existing interface, as happens on boiling chips and string used to make rock candy. The so-called Diet Coke and Mentos eruption is a dramatic example of this. Nucleation in boiling can occur in the bulk liquid if the pressure is reduced so that the liquid becomes superheated with respect to the pressure-dependent boiling point. More often, nucleation occurs on the heating surface, at nucleation sites. Typically, nucleation sites are tiny crevices where free gas liquid surface is maintained or spots on the heating surface with lower wetting properties. Substantial superheating of a liquid can be achieved after the liquid is degassed and if the heating surfaces are clean, smooth and made of materials well wetted by the liquid. Nucleation is relevant in the process of crystallization of nanometer-sized materials, and plays an important role in atmospheric processes. Nucleation is a key concept in polymer, alloy and ceramic systems. Some champagne stirrers operate by providing many nucleation sites via high surface area and sharp corners, speeding the release of bubbles and removing carbonation from the wine. Sodium acetate heating pads use cavitation voids caused by the deflection of a metal disc as nucleation centers for exothermic crystallization. Microtubule nucleation is the nucleation of microtubules, large rod-like structures found in eukaryote cells. This nucleation is not of a thermodynamic phase, and like other aspects of microtubule dynamics, it is an energy-consuming process. Classical nucleation theory. This is the standard simple theory for nucleation of a new thermodynamic phase, such as a liquid or a crystal. It should be borne in mind that it is approximate. The basic classical nucleation theory for nucleation of a new phase provides an approximate but physically reasonable prediction for the rate at which nuclei of a new phase form, via nucleation on a set of identical nucleation sites. This rate, R, is the number of, for example, water droplets nucleating in a uniform volume of air supersaturated with water vapor, per unit time. So if a 100 droplets nucleate in a volume of 0.1 m3 in 1s, then the rate R equals 1000. The description here follows modern standard classical nucleation theory. The prediction for the rate R is: where is the free energy cost of the nucleus at the top of the nucleation barrier, and kBT is the thermal energy with T the absolute temperature and Kb is the Boltzmann constant. Is the number of nucleation sites. J is the rate at which molecules attach to the nucleus causing it to grow. Z is what is called the Zeldovich factor. Z essentially the Zeldovich factor is the probability that a nucleus at the top of the barrier will go on to form the new phase, not dissolve. This expression for the rate can be thought of as a product of two factors. The first is the average instantaneous number of fluctuations that at the top of the nucleation barrier. This is the number of nucleation sites, multiplied by the probability that a nucleus of critical size has grown around it. Free energies and probabilities are closely related in general, by definition probability of a nucleus forming at a site. So if is large and positive, the probability of forming a nucleus is very low and nucleation will be slow. Then the average number will be much less than 1, that is, it is likely that at any given time none of the sites has a nucleus. The second factor in the expression for the rate is the dynamic part, which also has two parts. The first is the rate at which molecules add to the nucleus, increasing its size, and the second part is derived by assuming that near the top of the barrier the nucleus is effectively diffusing along the axis, and so nuclei at the top of the barrier can grow diffusively into larger nuclei that will grow into a new phase, or they can lose molecules and shrink back to nothing. The probability that they go forward is Z. To see how this works in practice we can look at an example. Sands and co-workers have used computer simulation to estimate all the quantities in the above equation, for the nucleation of ice in liquid water. They did this for a simple but approximate model of water called TIP5P/2005. At a supercooling of 19.5 C, that is, 19.5 C below the freezing point of water in their model, they estimate a free energy barrier to nucleation of ice of. They also estimate a rate of addition of water molecules to an ice nucleus near the top of the barrier of J equals 10^11 and a Zeldovich factor Z equals 10^3. The number of water molecules in 1 m3 of water is approximately 1028. Putting all these numbers into the formula we get a nucleation rate of approximately 1083s. This means that on average we would have to wait 1083s to see a single ice nucleus forming in 1 m3 of water at -20 C. This is a rate of homogeneous nucleation estimated for a model of water, not real water or we cannot growing nuclei of real water and so cannot directly determine the values of the barrier Ig, or the dynamic parameters such as J, for real water. However, it may be that indeed the homogeneous nucleation of ice at temperatures near 20 Celsius and above is extremely slow, and so that whenever we see water freezing temperatures of 20 Celsius and above, this is due to heterogeneous nucleation, that is, the ice nucleates in contact with a surface. Homogeneous nucleation is much rarer than heterogeneous nucleation. However, homogeneous nucleation is simpler and so easier to understand than heterogeneous nucleation, so the easiest way to understand heterogeneous nucleation is to start with homogeneous nucleation. So we will outline the classical nucleation theory calculation for the homogeneous nucleation barrier. To understand if nucleation is fast or slow, needs to be calculated. The classical theory assumes that even for a microscopic nucleus of the new phase, we can write the free energy of a droplet as the sum of a bulk term that is proportional to the volume of the nucleus, and a surface term, that is proportional to its surface area. The first term is the volume term, and as we are assuming that the nucleus is spherical, this is the volume of a sphere of radius. Is the difference in free energy per unit volume between the thermodynamic phase nucleation is occurring in, and the phase that is nucleating. For example, if water is nucleating in supersaturated air, then is the free energy per unit volume of the supersaturated air minus that of water at the same pressure. As nucleation only occurs when the air is supersaturated, is always negative. The second term comes from the interface at surface of the nucleus, which is why it is proportional to the surface area of a sphere. Is the surface tension of the interface between the nucleus and its surroundings, which is always positive. For small the second surface term dominates and the free energy is the sum of the n terms. Now the terms varies more rapidly within the term, so as small the term dominates and the free energy is positive while for large, the term dominates and the free energy is negative. This shown in the figure to the right. Thus at some intermediate value of the free energy goes through a maximum, and so the probability of formation of a nucleus goes through a minimum. There is a least probable nucleus occurs, that is, the one with the highest value of where. This is called the critical nucleus and occurs at a critical nucleus radius. Addition of new molecules to nuclei larger than this critical radius decreases the free energy, so these nuclei are more probable. The rate at which nucleation occurs is then limited by, that is, determined by the probability of forming the critical nucleus. This is just the exponential of minus the free energy of the critical nucleus, which is. This is the free energy barrier needed in the classical nucleation theory expression for above. Heterogeneous nucleation. Heterogeneous nucleation, nucleation with the nucleus at a surface, is much more common than homogeneous nucleation. Heterogeneous nucleation is typically much faster than homogeneous nucleation because the nucleation barrier Ig is much lower at a surface. This is because the nucleation barrier comes from the positive term in the free energy Ig, which is the surface term. For homogeneous nucleation the nucleus is approximated by a sphere and so has a free energy equal to the surface area of a sphere, for I(R2) times the surface tension I fluorine. However, as we can see in the schematic of macroscopic droplets to the right, droplets on surfaces are not complete spheres and so the area of the interface between the droplet and the surrounding fluid is less than. This geometrical factor reduces the interfacial area and so the interfacial free energy, which in turn reduces the nucleation barrier. Note that this simple theory treats the microscopic nucleus just as if it is a macroscopic droplet. In the schematic to the right the contact angle between the droplet surface and the surface decreases from left to right, and we see that the surface area of the droplet decreases as the contact angle decreases. This geometrical effect reduces the barrier and hence results in faster nucleation on surfaces with smaller contact angles. Also, if instead of the surface being flat it curves towards fluid, then this also reduces the interfacial area and so the nucleation barrier. There are expressions for this reduction for simple surface geometries. In practice, this means we expect nucleation to be fastest on pits or cracks in surfaces made of material such that the nucleus forms a small contact angle on its surface. Similar effects can cause precipitate particles to form at the grain boundaries of a solid. This can interfere with precipitation strengthening, which relies on homogeneous nucleation to produce a uniform distribution of precipitate particles. Computer simulation studies of simple models. The classical nucleation theory makes a number of assumptions. For example, it treats a microscopic nucleus as if it is a macroscopic droplet with a well-defined surface whose free energy is estimated using an equilibrium property, the interfacial tension I fluorine. For a nucleus that may be only of order 10 molecules across it is not always clear that we can treat something so small as a volume plus a surface. Also nucleation is an inherently out of thermodynamic equilibrium phenomenon so it is not always obvious that its rate can estimated using equilibrium properties. However, Modern computers are powerful enough to calculate essentially exact nucleation rates for simple models. These have been compared with a classical theory, for example for the case of nucleation of the crystal phase in the model of hard spheres. This is a model of perfectly hard spheres in thermal motion, and is a simple model of some colloids. For the crystallization of hard spheres, the classical theory is a very reasonable approximate theory. So for the simple models we can study CNT works quite well, but we do not know if it works equally well for say complex molecules crystallizing out of solution. The spinodal region, phase transition processes can also be explained in terms of spinodal decomposition, where phase separation is delayed until the system enters the unstable region where a small perturbation in composition leads to a decrease in energy and, thus, spontaneous growth of a perturbation. This region of a phase diagram is known as the spinodal region, and the phase separation process is known as spinodal decomposition and may be governed by the Knaer-Hilliard equation. Experiments on the nucleation of crystals. It is typically difficult to experimentally study nucleation. The nucleus is microscopic, so the nucleus is too small to be directly observed. In large liquid volumes there are typically multiple nucleation events, and it is difficult to disentangle the effects of nucleation from those of growth of the nucleated phase. These problems can be overcome by working with small droplets. As nucleation is stochastic, many droplets are needed so that statistics for the nucleation events can be obtained. To the right is shown an example set of nucleation data. It is for the nucleation at constant temperature and hence supersaturation of the crystal phase in small droplets of supercooled liquid tin. This is the work of Pound and Lemaire. Nucleation occurs in different droplets at different times, hence the fraction is not a simple step function that drops sharply from 1 to 0 at one particular time. The red curve is a fit of a Gompertz function to the data. This is a simplified version of the model Pound and Lemaire used to model their data. The model assumes that nucleation occurs due to impurity particles in the liquid tin droplets, and it makes the simplifying assumption that all impurity particles produce nucleation at the same rate. It also assumes that these particles are Poisson distributed among the liquid tin droplets. The fit values are that the nucleation rate due to a single impurity particle is 0.02 per second, and the average number of impurity particles per droplet is 1.2. Note that about 30% of the tin droplets never freeze. The data plateaus at a fraction of about 0.3. Within the model this is assumed to be because, by chance, these droplets do not have even one impurity particle, and so there is no heterogeneous nucleation. Homogeneous nucleation is assumed to be negligible on the timescale of this experiment. The remaining droplets freeze in a stochastic way, at rate 0.02 per second if they have one impurity particle, 0.04 per second if they have two, and so on. This data is just one example, but it does illustrate common features of the nucleation of crystals in that there is clear evidence for heterogeneous nucleation, and that nucleation is clearly stochastic. Modern technology. Nucleation is a topic of wide interest in many scientific studies and technological processes. It is used heavily in the chemical industry for cases such as in the preparation of metallic ultra-dispersed powders that can serve as catalysts. For example, platinum deposited onto TO2 nanoparticles catalyzes the liberation of hydrogen from water. It is an important factor in the semiconductor industry, as the gap width in semiconductors is influenced by the size of metal nanoclusters. As another example, understanding calcium carbonate nucleation could help scientists control its formation to keep carbon dioxide from getting into the atmosphere. Instruments such as the bubble chamber and the cloud chamber rely on nucleation. See also, microtubule nucleation, references.